Hi everyone, this video is for Chapter 5, Lesson 4, Writing and Solving Proportions. Your learning target is to be able to use proportions to solve ratio problems. And your success criteria is I can solve proportions using various methods. I can find a missing value that makes two ratios proportional. And I can use proportions to solve and represent real-life problems. So to solve a proportion, we just look at multiplication or division, and we look to apply a factor between the top numbers or the bottom numbers. So for example, we think 2 times what gives us 8? 2 times 4 gives us 8. So then 3 times 4 gives us 12. And we know that 3 halves is 1 1/2. And 12 eighths is also 1 1/2. For this next one, 7 times 3 gives us 21, so 5 times 3 would give us 15. Here's 2 more examples. Let's make sure we get these written down in our notes. I see that we have 12 to 36, so I could apply a factor of 3 there. 12 times 3 is 36. So therefore, 5 times 3 is 15. And for the second one, I notice that I have numerators. 6 times 7 is 42. So some number times 7 is 35. 5 times 7 is 35. Another way you could think of this is if you went the opposite direction. 42 divided by 7 is 6, and so therefore 35 divided by 7 is 5. Now it's your turn. Try it. Solve the proportion using multiplication or division, and then push play when you're ready. In this first example, I see 5 times 4 would give me 20. So 8 times 4 would be 32. 7 times 2 is going to be 14. So what number times 2 is 10? That would be 5. And now in this third one, let's work backwards. 8 times 3 is 24. So what number times 3 would give you 21? That would be 7. Now that we're getting the hang of using multiplication or division to find and apply a factor to make equivalent ratios, let's take it a step further where we have to do multiple steps. This is called using scaling. So in this first example, I want you to notice that 12 and 16, those aren't compatible. I don't know what I could multiply 16 by to get 12. So what I want to do is I want to turn 20/16 into an equivalent fraction where the denominator is compatible with 12. So essentially what we're doing here is we're looking for common multiples. If I were to multiply 20/16 by 3 over 3, I get 60/48. Now I can get rid of this, and 60/48 is equivalent to d over 12. Now I'm in good business because I know that 48 divided by 4 is 12. So I can then do 60 divided by 4, and I get 15. In this second example, I want to show you that instead of scaling up, like we did in this previous one, where we went from 20/16 to 60/48, you could also scale down, which in other words, that's just simplifying. If we divide by 16 over 16, we just have a half. So our new proportion is 5 over n equals 1/2. Well, in this case, 1 times 5 is 5. 2 times 5 is 10. And we know that 5/10 is equivalent to 1/2. Here are 3 more try-its for you, just to make sure that we are really getting a good understanding of solving these proportions. In this first one, we're going to need to do something called scaling, because 6 and 9 are not nice compatible numbers. However, if we multiply times 2 over 2, we get 12/18. And I can see that that works easily. 6 times 3 is 18. So what number times 3 gives us 12? That would be 4. Similarly, in question number 5, I could multiply by 3 and get 30, and multiply 12 times 3 to get 36. And now that I have that, now I can see that 15 times 2 is 30. So what number times 2 gives me 36? That would be 18. And question number 6 is a little easier. 5 times 2 is 10, so 3 times 2 is 6. Now, honestly, I would prefer that you just use your math knowledge and your common sense to solve proportion problems the way I've been showing you. However, there is another strategy called cross multiplication. And what that means is you're just going to multiply 7 times 8. And that's going to equal 10 times x. So what we have here is 56 equals 10x. So you can divide both sides by 10. The 10s cancel out, and you end up with x equals 5.6. Situations where this cross product strategy is going to come in handy is when you do have decimals such as this. So we'll multiply 7.2 times 1.8 and that's going to equal 2.4 times k. So now when we solve this, we get 12.96 equals 2.4k. Divide both sides by 2.4. The 2.4's cancel, leaving you with just k. And 12.96 divided by 2.4 is 5.4. So then here's 3 more for you to try to solve on your own. Use either the multiplication division strategy that I showed you first, or in question number 9, for example, if you'd like to use the cross products property, you can use that one as well. Then push play when you're ready. So I'd say for number 7, let's just use multiplication to find the factor. 7 times 4 is 28, so 2 times 4 is 8. Similarly, in number 8, we could go, let's go right to left on this one. 6 times 2 is 12. So what number times 2 is 5? 2.5, 2.5. Or if you wanted to do the cross product strategy for that one, I'll show you that as well. 6 times 5 is 30. That equals 12y. So you divide both sides by 12. And you get 30 divided by 12. And 30 divided by 12 is 2.5. For this last one, I would suggest using the cross product strategy. 6 times 40 is 240. Z plus 1 times 15. That's going to be your other cross product, and that's going to require you to distribute. So you end up with 15Z plus 15, and that equals 240. And now you solve. And so on the left side, we end up with 225. On the right side, we end with 15Z. And then divide both sides by 15. Z equals 225 divided by 15, which is 15. In example number 4, we just have a bit of a story problem. Find the value of x so that the ratios 3/8 and x over 20 are equivalent. So it says for the ratios to be equivalent, the values of the ratios must be equal. So find the value of x for which 3/8 and x over 20 are equal by solving a proportion. So what that means if it says by solving a proportion is we need to look at this as an equation, and we need to solve for x just like we did in chapter 4. So what we would do is we'd multiply by 20. 20 divided by 20 is 1, so you're just left with x. Whatever you do to one side, you have to do to the other. So you would multiply by 20, and then here you could cross simplify. 4 goes into 8 twice, 4 goes into 25 times, and you end up with 15 halves, or you could say 15 halves is 7.5. So now I'd like to show you another example, and let's try to make sure we get this one written down. Solve this proportion as an equation. So we have got our equation set up here. We're going to multiply both sides by 12. 12 over 12 cancels, so we're just left with n. On the other side, we'll write 12 as a fraction, 12 over 1. And then we'll cross simplify. Oh, and I can see that I could have actually factored out 4, because now 2 will go in here, and 2 will go in there as well. So I have 3 times 35. I get 105 sevenths. 105 divided by 7 is 15. So we would say that n is 15. And now it's your turn. Go ahead and try these next 3. So let's set this up. 2/4 x over 6. We'll multiply both sides by 6. 6 over 6 cancels, so we have x. And on the other side, we have 12/4. So x equals 3. For number 11, we have x over 5 and 8 halves. So we'll multiply both sides by 5. 5's cancel. So we end up with x is 40 over 2. X equals 20. And then we have 4 to 3 equals 10 over x. Now in this last example, number 12, you're going to notice that the variable's on the bottom. So in this situation, what we can do is we can go back to our cross product strategy where we do 3 times 10 is 30. 4 times x is 4x. And we can divide by 4. The 4's cancel. And we're left with 30 divided by 4. 30 divided by 4 is 7.5. For example 5, a chef increases the amount of ingredients in a recipe to make a proportional recipe. The new recipe has 6 cups of black beans. Which proportion can be used to find the number x of cups of water in the new recipe? So we're going to be comparing cups of water to cups of black beans. And the recipe's telling us that this new recipe is now going to have 6 cups of black beans. So 6 cups of black beans compared to 1.5 cups of black beans. That's telling us that whatever expression that whatever proportion we choose down below, the 1.5 and the 6 are going to have to be across from each other. So what I notice right away, 1.5 and 6 in A, those are opposite each other. 1.5 and 6, those are opposite of each other. 1.5 and 6, those are over each other. So it's going to have to be D. 1.5 and 6, those are representing the beans. And the 2 on the bottom, that is representing cups of water, which is right here in the original recipe. So I want you to try it now. I want you to write a proportion that can be used to find the number of tomatoes in the new recipe. Look in your notes at the previous example that I just did. I'll help get you set up here. You're going to start with the 1.5 compared to the 6. Okay. And now you're going to write a proportion that can be used to find the number of tomatoes in the new recipe. Then go ahead and push play when you're ready. Okay, so I got you started here. What we don't know is how many tomatoes will be in the new recipe. The new bigger recipe was going to be the one calling for the 6 cups of black beans. The 1.5 cups of black beans, that was the original. So you'll look at that original bean soup recipe and you'll see that there was 1 tomato used. So now we have our proportion. 1.5 times 4 gets us to 6. So 1 times 4 gets us to 4. So in the new recipe again, we will have 6 cups of black beans and 4 tomatoes. Our final example, number 6, it says a Titanosaurus's heart pumped 50 gallons of blood for every 2 heartbeats. How many heartbeats did it take to pump 1,000 gallons of blood? So you're given the rate at which the Titanosaurus's heart pumps. Because all the rates you can write using this relationship are equivalent, the amount of blood pumped is proportional to the number of heartbeats. You are asked to find how many heartbeats it took to pump 1,000 gallons. So the ratio of heartbeats to gallons of blood is 2 heartbeats for 50 gallons of blood. The number X of heartbeats for every 1,000 gallons of blood can be represented by the ratio of X to 1,000. So we'll use a proportion to find the value of X for which 2 over 50 and X over 1,000 are equal. You could use multiple different strategies. Some of you, when you get to this point, you'll look at this problem and you'll see 50, and you'll know that 50 times 20 is 1,000. So 2 times 20 is 40. And then another strategy that you could use is your cross product strategy, where you do 2 times 1,000 and you get 2,000. And then 50 times x is 50x. Divide both sides by 50. And you end up with x equals 40. And then the last method you could use is similar to what I showed you originally, but you're just putting it in a table. And then you're identifying that 50 times 20 is 1,000 and 2 times 20 is 40. So let's dig deeper. 2 boats travel at the same speed to different destinations. Boat A reaches its destination in 12 minutes. Boat B reaches its destination in 18 minutes. Okay, so we're going to say A takes 12 minutes. B takes 18 minutes. Boat B travels 3 miles further than A. So here's the time, and here's the distance. The distance for A is just D for distance. Boat B travels 3 miles further, so that's going to be D plus 3. So then how fast do the boats travel? Justify your answer. So what we're going to do here is we're going to set up a proportion. We're going to set this up as D over 12, because that is representing our relationship or our ratio for boat A. Then for boat B, we're going to set up D plus 3 over 18. And from here, we're going to solve. We'll use our cross product. 12 times D plus 3. And here we get 18D. We'll distribute, and we get 12D plus 36 equals 18D. We're going to take away 12D from both sides. And we get 36 equals 6D. And then we're going to divide by 6. And we get D equals 6. So the distance is 6. So D plus 3 would be 9. From here, we're going to write this as a rate. We have labels of minutes and miles. Let's think about what would make more sense. Would it make more sense to say miles per minute or minutes per mile? It would make more sense to say miles per minute. And I say that because when we talk about speed, we often talk about meters per second, feet per second, miles per hour, where the time goes on the bottom. So here we'd have 6 miles per 12 minutes, and that would reduce to a half. And we also have 9 miles per 18 minutes, which would reduce to a half. So we'd say 1 mile per 2 minutes. Or we could say 1/2 mile per minute. We finally reached the end of this one. You burn 35 calories every 3 minutes running on a treadmill. You want to run for at least 15 minutes, but no more than 30 minutes. What are the possible numbers of calories that you'll burn? So we need to set up our ratios or set up our proportions. we're going to set this up as 35 calories per 3 minutes. And it says you want to run for at least 15 minutes. So if you ran for 15 minutes, how many calories would you burn? Let's set up the same. But this time, let's say you go for 30 minutes, and we want to find out how many calories you'd burn. So I see right away I don't need to do cross product or anything. 3 times 5 is 15. So 35 times 5 is going to give me how many calories I'd burn. And 35 times 5 is 175. I don't need cross product. I don't need to solve with an equation. I can just look here and I can use multiplication. 3 times 10 is 30. 35 times 10 is 350. So the question says, what are the possible numbers of calories that you could burn? You could burn between 175 and 350 calories. So that wraps up the notes lesson for Chapter 5, Lesson 4. If you have any questions, please stop and see one of your teachers and ask for help. Otherwise, hope you're doing well.